Hi everyone, thank you for the invitation to the Data Shape seminar. I'm going to present you the work I did with Wolfgang Polonik and Krishna Kumar Balasubramanian at UC Davis during an internship I did from March to August. And this is the work I'm going to continue during the following 3 years of my PhD. I've been interested in studying topological regularization for regression and manifolds. So I am studying a regression framework on a manifold M of dimension d in some large ambient Euclidean space. As for a regression setup, we observe a n sample xi, yi, where the xi are points of the manifold, and the yi are real numbers. They are labeled associated to the xi. We assume that the data are modeled as yi equal a function of xi plus random noise epsilon I, where the noise is independent on each entry xi. And the goal here is to retrieve the regression function f in order to, when given a new point on the manifold, predict its label yi, its real label. The idea that motivates this work is twofold. One aspect is to approximate the regression function as a linear combination of the eigenfunctions of the Laplace Beltrami operator, which is a differential operator on the manifold. So we want to use the geometric properties of the space the data lie onto. And the other aspect of the work is to introduce a topological penalty in order to prevent overfitting of the data and to introduce topological a priori. The class of regression problems on manifold is becoming more and more important. So, for instance, we can think of data that lie on the sphere, on the globe. So data that represent the temperature, the wealth, the concentration of some ecological quantities, some measurements of things on the sphere, on the globe, or we can consider the same study on states or regions or countries. This type of things was small dimension manifold. Or we can think of maybe more developed examples. So for instance, if we are studying a subset of images or 3D volumes. So for instance, if we study medical images, we won't study the whole set of images. We will only restrict ourselves to a submanifold of images. If we are studying images of brains, for instance, we will only look at the manifolds of pictures of brains, which is a very small subset of the global set of images, of the ambient set of images. So I'm going now to develop the model, be more precise on the model. Then I will discuss all the theoretical guarantees we have. So first on the Laplacian eigenfunctions and also on the statistical model we introduce. Then I will present a few experiments and maybe, if I have time, discuss the topological penalty, why is it used, and the type of results we would like to have regarding this topological penalty. As for the model, so we have to assume a lot of hypotheses on the manifold M. Basically, that it's a nice, kind, well-behaving manifold. So, for instance, that it's closed, compact, that it's a Riemannian submanifold of RD, and that it has no boundary. On this manifold, we introduce the Laplace Beltrami operator, which is the divergence of the gradient of the vector field on an analogous fashion to the Euclidean case. And its expression in local coordinates is given here, which is basically a second-order derivative terms, second differential operator on a function. I don't think we have to get into details of what this operator is doing, and we can think of it really by analogy with the Euclidean case. We notice that here G is the metric tensor that appears in the expression. And if we look at the Euclidean space, G is the identity matrix, and we retrieve the same Laplacian, so the trace of the Hessian matrix. By convention, we have a minus sign in front of the divergence of the gradient, and it's just to ensure that the spectrum is non-negative. Given the hypothesis on the manifold, we have a nice properties following on the operator delta. So delta is a positive semi-definite self-adjoint operator. Because of that, it has a discrete, real, non-negative spectrum. with finite dimensional eigenspaces. So we can denote its eigenvalues by lambda 0, lambda 1, etc. And this sequence tends to infinity. And for each lambda I, we have several eigenfunctions that have a lot of regularity properties. So they are C infinity, but we know a lot more about them, especially bounds on their Hölder norm, on their Sobolev norm. And those functions are very smooth. So this smoothness, this well-behavedness of the eigenfunctions is one reason why we would use them in order to perform a regression. We also, one way to think about it, so we could, some people know justification in physics of why it's a good idea to approximate a function by the eigenfunctions of the Laplace Beltrami on the manifold. We can look at a simple example in one dimension. So if we look at the segment 0, 1, the Laplace Beltrami operator is the second order derivative. And so the eigenfunctions are simply the sines or the cosines. It kind of depends on the boundary conditions. And it's basically the Fourier basis. And when given a Euclidean space, like a square, a cube, the eigenfunctions will be the Fourier basis, which we know are nice functions to perform regression. They can be nice functions. They are nice to do compression, for instance. And here we can think of this Laplace Beltrami operator eigenfunctions as a way to generalize the Fourier basis to general manifolds. And here the idea is to approximate the regression function f by a finite sum of the first p eigenfunctions. So we have to truncate the eigenbasis at a level p, kind of arbitrary level p, and then find the parameter theta so that we find a function that is as close as possible as f. More precisely, we want this function to be closed in L2 norm, so we are solving a penalized least square on the data xi, yi. And as classically in statistics, we are introducing a penalty term, or a regularization term, omega of g, and lambda is a trade-off parameter, which will tune the amount of penalty compared to the amount of fitness to the data. The problem here is that this Laplace Beltrami operator is a complicated operator. Computing its spectrum is hard. We would have to solve PDEs. And what's the thing is, as I said in the introduction, sometimes the manifolds are unknown. For instance, if we look at subsets of images or 3D volumes, the manifold is unknown. So we can't really compute the Laplace Beltrami operator on them, and let alone its spectrum. So the way we use to bypass this problem is actually quite simple, is to build a graph on the data points, and then to compute the Laplacian of the graph. So the graph I chose in most experiments is a Gaussian graphs. So it's an undirected graph with an edge between each point, and the weight is this factor wij, which is a Gaussian, some constant times exponential minus the distance square between the 2 points divided by 40, and t is a scaling parameter which is meant to tend to 0 in order to retrieve local properties. Here we can notice that the distance between xi and xj is the Euclidean distance, the distance of the ambient space, and not the metric on the manifold, because of course we don't necessarily know the manifold. And it's not a big deal actually, because we still have results of convergence of the spectrum with this Euclidean distance. And what we call the graph Laplacian is the matrix of degrees minus this matrix of weights W. And the matrix of degrees D is a diagonal matrix where the entry I is the sum over a line for the matrix W. This is the unnormalized Laplacian, and we have the normalized Laplacian, which is the same thing multiplied by the invert of the square root of D on the left and on the right. This matrix is symmetric positive and is therefore diagonalizable in a north normal basis. And we can then replace the eigenfunctions of the Laplace Beltrami operator by the eigenvectors of this matrix L to perform the regression. So we are basically replacing the eigenfunctions of some complicated operator by the eigenvectors of some matrix, where everything is easy to compute, you could say. So here are on the square, the example of the graph Laplacian eigenvectors that were computed here on a KNN graph. So we observe that these functions are quite similar to cosines and sines and products of cosines and sines. So basically oscillating functions that remind us of the Fourier basis, with an interesting behavior as the index of the eigenfunction becomes high. So this is the first aspect of the project, is to perform a regression using the Laplace Beltrami eigenfunctions or their graph approximations. The other aspect of the problem is the penalty term omega. And this penalty term omega, we will introduce a topological penalty. So this idea has been studied before in experimental papers, but there's not many theoretical guarantees about why a topological penalty is working. So this is kind of the goal of this project, to provide theoretical guarantees about this penalty. So I'm sorry if most of you are already familiar with homology and persistent homology, but I'm going to give a very quick reminder. So when looking at a topological space X, the homology of X is a set of abelian groups, which are invariant by homeomorphism. And we can think of those groups as Z over 2Z vector spaces. And the zero homology group is generated by connected components. And the kth homology group is generated by k-dimensional holes or k-dimensional cycles. And we recall that a hole can be thought as the boundary of a k plus 1 dimensional body. So a 1-dimensional circle is the boundary of a disk, and so on. So for instance, if we have a circle, then its first group of homology here is Z over 2Z. If we give ourselves an n-dimensional sphere, then its nth group of homology is Z over 2Z, because it has one body, one feature of dimension n, and no feature of dimension between 1 and n minus 1. So all the k homology group of dimension between dimension 0 and n are trivial. We can think of a more interesting examples. So the 2-dimensional torus. If we look at the zero homology, it has only one single connected component. So its zero homology group is Z over 2Z. It has one single 2-dimensional hole, which is the void inside the surface of the torus. So its second homology group is Z over 2Z. And for the one cycles, it's slightly more interesting, since the torus has two independent loops on itself, the red and the blue loops in the picture. And therefore, its first homology group is Z2 times Z2. And we denote the dimension of the k homology group by beta k, and it's called the kth Betti number. This was homology. What we're going to use is persistent homology. So basically, we are giving ourselves a nested family of topological spaces, xt, where t can go from t is a parameter, a real number parameter. And the idea behind persistent homology is to consider all the homology groups and note in diagrams when they are created and when they disappear. So we have this object called a persistence diagram, and for each feature that appears at some point when the parameter t goes from minus infinity to plus infinity, we note in the x-axis where it's born, and on the y-axis when it dies. So for instance, if we look at the space here, this disk with 4 holes punctured on itself, and the filtration, the nested family of topological spaces is the thickened version of this space. So this space with balls center on each point. We have one connected component all the times that exists at time 0 and never dies, or stated otherwise, that dies at an infinite time. So hence the red point on the diagram. where here the line is the infinity. And we have, at time 0, we have 4 one-dimensional holes, one around each, 4-dimensional cycles, excuse me, one around each hole in the disk. And they are all born at time 0. And as we thicken the space, the holes will get filled one by one. And this is why we have those green points corresponding to one homology, and they all die at successive times. Here we will look at a very specific case of persistent homology, and this is the persistence of the sublevel sets of functions. So I will make an abuse of language talking about the persistence of a function is actually the persistence of its sublevel sets. So here I'm giving an example for a one-dimensional function. Here we have, so when the sublevel sets are, when t is between minus infinity and a, the sublevel sets are empty. So there is nothing to say about their homology. As we pass the first minimum, the global minimum of the function at point A, then the sublevel set has one connected component. Then as we pass through point B, we have a second connected component that is born. And when we pass the point C, we kill the previous connected component. We actually merged the first two connected components. And by convention, we say that it's the youngest which die. So there is a component that is born at time B and dying at time C. Hence, we have a point of coordinate BC in the persistence diagram. As we go along the filtration, we have at point D, we create a new connected component and we kill it at time E. So here's this point DE. And the first connected component born at time A actually never dies. So it dies at infinity here. I recall that what we call the persistence of a feature, so of a point in the diagram, is its lifetime, so its death time minus its birth time. And the persistence of a function is actually the persistence of its diagram, of its persistence diagram. And this is the sum over all points in the diagram of their persistence. One convention here is that if a feature has an infinite persistence, we won't say that it dies at infinity, but we will say that it dies at the maximum of f. And since we only study continuous functions and compact manifolds, functions have maxima. And so that we are not studying infinite persistence, only finite quantities. The idea why we are doing that is that functions that oscillate a lot, they are functions we want to discard because these functions will overfit the data. I will discuss more about this, but this is the leading idea. The functions that oscillate a lot, they have a lot of critical points, a lot of minima and maxima and saddles. And if they have a lot of critical points, they will have high total persistence. So we see that here the persistence of the function is its maxima minus its minima. So if it oscillates a lot, it has a lot of maxima and a lot of minima, and therefore a high total persistence. And here the penalty we introduce finally is a weighted lasso. So the penalty omega of theta, of the parameter theta we want to estimate, is the sum over all the eigenfunctions of the absolute value of theta I times the persistence of the corresponding eigenfunction. So if I'm going from scratch, what we are doing in this project, we have data points x and labels y we want to predict, we want to learn. In order to do so, we build a graph on x. Then we compute the first p eigenvectors of the corresponding graph Laplacian. For each one of these eigenvector, we compute its persistence on a discrete triangulation of the manifold. So in my experiments, I build the Delaunay complex on the points, and then I computed the persistence of the eigenfunction, the eigenvector applied to this Delaunay triangulation. Then we introduce a design matrix, which is where the entry ij of the design matrix is the jth eigenfunction applied to point I. So for the eigenvector, it's the ith coordinate of the jth eigenvector. And we divide everything by the persistence of the eigenvector. So we basically divide each column by the persistence of the corresponding eigenvector. The column of the design matrix are the eigenvectors, and each one is divided by the individual persistence. And given this new design matrix x tilde, this change of variable, then we only have something called a lasso, which is a very simple optimization problem, where we want to find theta minimizing this quantity, which is the L2 norm plus a regularization term in L1 norm. I am now going to discuss the theoretical guarantees we have in this model. So we are replacing the eigenfunctions by a discrete counterpart, the eigenvectors of a graph Laplacian. We have results that state that we are allowed to do so somehow. So I'm going to be more precise. So imagine we consider Gaussian weights and make simple assumptions on how the x are sampled on the manifold. So we can extend to more general settings, but I think it's best to keep things simple. The main result that we can find in the literature is that we have a spectral convergence of this graph Laplacian towards the Laplace Beltrami operator. And we have a double limit setting. So this convergence appears when the number of points n tends to infinity and when the scaling of the graph tends to 0. So basically when we are looking at localized version, when the graph becomes more and more local at the data points, that becomes more and more. And all those results about spectral convergence, they hold usually in L2 norm, and they are probabilistic results. And the convergence holds in probability in most cases. So first of all, in order to get rid of this double limit, we have to scale the parameter t in a certain way so that t doesn't decrease too quickly compared to n. So one example is to take this scaling written here. And the problem here of this convergence is that the Laplacian matrix is of size n because it's built on n points. Therefore, the eigenvectors are of size n, of dimension n. And we're looking at the behavior when n tends to infinity. So all the eigenvectors live in different spaces. They all have different size. So we cannot compare eigenvectors between them, and we cannot compare an eigenvector towards the limit object, which is a function of L2 of m. So to get rid of this, to bypass this difficulty, we have to first take the eigenvector, consider a piecewise constant function on the manifold. So we have the data points, and to each of these data points, there is a value of the eigenvector attached. We build the Voronoi complex on the manifold, and within a Voronoi cell, we construct a function u bar, so that u bar is constant on each Voronoi cell to the value of the eigenvector at the center of the Voronoi cell. So u bar is a piecewise constant function, and then we smoothen this function using an interpolation operator I, which is a kernel smoothing of this piecewise constant function u bar. And the results we have convergence of the eigenvalues in probability. So the ith eigenvalue of the graph Laplacian converges towards the ith eigenvalue of the Laplace Beltrami operator. And the thing that we are interested in is if we give ourselves a normalized eigenvector, if we consider the ith eigenvalue, we look at the corresponding normalized eigenvector. Then there exists a normalized eigenfunction of the Laplace Beltrami operator corresponding to the same limit eigenvalue, such that the interpolation of this vector minus the limit function phi I is of order something decreasing towards 0 as n tends to infinity. And this, we recognize actually the rate, the scaling Tn. Okay, so this result is a first nice result that we can find in the literature, but this is somehow a weak result. So the first thing is that if we look carefully at the theorem for eigenfunctions, we don't have that each eigenvector converges towards a specific eigenfunction. We have that given an eigenvector, there exists a limit eigenfunction corresponding to the same eigenvalues, sort of. This means that if we have multiplicity of the eigenspaces for the Laplace Beltrami operator, we cannot have the convergence of the eigenvectors. We only have convergence of the eigenspaces. And we will have basically that all the eigenspaces associated to the ith eigenvalue will converge towards the space of the ith eigenvalue of the Laplace Beltrami operator. And the second limitation is that the result holds in L2 norm. So the problem why it holds in L2 norm is that one of the goals of this project is to establish consistency results, statistical consistency results for the model. And one of the first steps to do so would be to prove that the persistence converge, that the tools we are using have a sense as n tends to infinity. So basically, when we are given, when we look at the persistence of a vector, of an eigenvector, we want this object to converge. To prove that, it would be nice to use stability results, stability theorems, and they all hold for L infinity norm. And they don't hold in L2 norm. So it's easy to convince ourselves that we can build a function with a very small L2 norm and a very large persistence. So the idea that is still under progress, still under development, is that if we scale appropriately n and t, it's possible, I think, that the interpolations of the eigenvectors, so the smoothing of the vector, are uniformly Lipschitz for a given eigenvalue. And if it's uniformly Lipschitz, then we have equicontinuity of this sequence I, phi, I, n, t, n. And if a sequence is L2 and equicontinuous, then we will have, by some sort of Ascoli theorem, some variation of Ascoli theorem, the convergence in infinity norm, the uniform convergence. But this is still under progress as for today. We can now look at some examples of the persistence of the real eigenfunctions to see the object we are penalizing. So in the square, the eigenfunctions are products of cosines on each variable, and there is a separation of variables. And the corresponding eigenvalue is n squared plus m squared. And if we plot the persistence of the eigenvectors, eigenfunctions, ordered by increasing eigenvalues, we observe this shape of the curve. So it's basically an increasing trend. So the higher the eigenvalue, the more oscillations we have. But it's not that simple because we have an oscillating behavior. My interpretation of this phenomenon is that the oscillations, we can see that they are not really oscillations. There is no period, and the period, if we can say this word, is becoming larger and larger. So here, the period is actually what's happening within one eigenspace. Here, the eigenspaces have a dimension larger than one. They have multiple dimension, which is written here. And within one eigenspace, the functions will have a different persistence. So this is also one issue of this, the spectral convergence theorem, is that if we prove the convergence of the eigenspaces, we cannot derive a result on the convergence of the persistence. Those results will only hold for manifolds where all the eigenspaces of the Laplace Beltrami operator are of dimension 1. So one aspect of this problem, we can see that it's interesting to penalize the persistence because it's going one step further than just penalizing the eigenvalue. So we could think, if we want to penalize the oscillations, we could look at the eigenvalue, but here we are going one step deeper in the analysis by penalizing within the eigenspaces. And we see that within the same eigenspace, there are some big differences of persistence. So it would be here maybe more interesting to just penalize to maybe just keep the lowest persistent function on all the eigenspaces rather than just keeping the functions that have a small eigenvalue. We observe the same phenomenon on the sphere, where we have this kind of trend for the eigenvectors and oscillating behavior, because for the sphere we also have the eigenspaces have multiple dimension. And I wrote the case of the sphere because in this case the Laplace Beltrami operator is simple to write. It's just the Euclidean Laplacian of the ambient space applied to a function, to a normalized function, to the function projected on the sphere. So this is for the guarantees we have on spectral convergence and the preliminary study on persistence. One thing we would like to develop are consistency results. So one result we have proved in this during this project is the consistency of the model while looking at the true eigenfunctions. So not the graph approximation. So this is kind of the first step. So we basically have that if we express the data, if the data are generated as a combination of the first p eigenfunctions plus some random noise, we have proven that the covariance matrix tends to some symmetric definite positive matrix, and therefore we have the asymptotic consistency of the estimated parameter of the lasso. So, which means that when the number of points tend to infinity, if the trade-off parameter is of order square root of n, then the parameter we estimate converges. More precisely, the difference between the estimated parameter and the true parameter that we want to find, this multiplied by square root of n converges. So this is called a consistency result. The other type of results we would be interested in are fixed n results or oracle inequalities. So for instance, we have this type of results developed from papers by Pascal Massard, where we basically have that if the trade-off parameter verifies some hypothesis, which here depends on the persistence of the eigenfunctions, in the case of the weighted lasso we study here. F here is the regression function, and the function we estimated doing the lasso, so the g hat function, will be close to the function, the solution of the lasso, but with no noise of the true solution of the lasso, plus some term that depends on the trade-off and on the noise sigma. Maybe one thing which is also under investigation is that we would like to improve these fixed n results by using results on the regularity of the phi I. So maybe results on the Hölder norm or the Sobolev norm of the phi I being bounded, and therefore the metric entropy of this class of functions or of balls of this class of functions being small. But this is also still under investigation. And all these results are for consistency with a fixed p. So making p tend to infinity will be the next step. And here what I wrote here is that we shown the consistency for the true eigenfunctions of the Laplace Beltrami operator. And the next step would be to prove it for the estimated eigenvectors, for the eigenvectors of the graph Laplacian. So first of all, we would have to prove the result on the persistence, that the persistence of the vectors converge. But then we still assume that the data are simulated as a linear combination of the first p true eigenfunctions. And we estimate the source, the target vector y, by the eigenvectors of the graph. And therefore, we would have that the y is equal to x bar times theta star plus a term that kind of tend to zero, somehow tend to zero by spectral convergence, plus the noise epsilon. And we would have to study the consistency of this on this model. Okay, so now I'm going to present you the one experiment I did, and that maybe give a first insight of what we can expect from this model. So I also tried experiments on toy data, simulated data on the square, the torus, the sphere, and they gave promising first results. So we had that basically using this graph Laplacian approach was doing a good job, and penalizing the persistence was also something of interest. But for this talk, I'm going to give a more interesting example. So we studied here a subset of images, a subset of L2. The database has 72 images of the same object, which is a cat raising its paw. And this object is rotated by increments of 5 degrees. So we have 72 images of the same cat, but rotated. And the goal here is to learn the rotation angle of the image. So when given an image of this cat rotated by, let's say, 55 degrees, we want the algorithm to say this cat is rotated by 55 degrees. And the algorithm has never seen the cat rotated by 55 degrees before, only by some other degrees. Here, the images lie on in R 16,384. They are small images of size 128 pixels. But we are, of course, not studying this entire very big vector space, but only a subset of it, and it's actually a one-dimensional submanifold, because we only have 1 degree of freedom as how to go from one cat to the other, and it's the rotation of the cat while taking the picture. We here built a Gaussian weighted graph, and the distance we used is the L2 metric, the L2 norm between two images. So once again, the metric of the ambient space, and that's the metric on some manifold on images, which could be possible here, but I kept things simple. So here is the aspect of some eigenfunction of the graph Laplacian, computed as a function of the image, so that we represented by its degree. So the first case is when the scaling parameter tends too quickly to 0, because here we have a small database, we have a small number of images, so we must remain careful for the scaling parameter not to tend too quickly to 0. And here, these are the examples of eigenfunctions where the scaling parameter t is equal to 10. So this kind of, as the index of the eigenfunction grows, we observe that the eigenfunctions are more and more localized, and this kind of reminds me of wavelet basis. So there might be something to dig up on this, but I don't have any more interpretation on why we have such a shape of the eigenfunction. So the results we observe here is that basically, if we compare this graph Laplacian approach with the usual Lasso, but performed on the very large Euclidean space, well, we have quite good reconstruction results, especially when we look at at reconstruction and not at generalization. So basically, when we have a big train set and a small test set, we are doing a good job with the Laplacian, but not as good as the Euclidean Lasso when we want to generalize the results. We notice that we have, of course, reduced the dimension of the problem, going from a space of dimension 16,000 whatever to a space of dimension roughly 60, so the number of images. Here we observe bad generalization properties because, as we've seen before, the eigenfunctions are oscillating functions. And oscillating functions don't usually do a great job at generalizing to new data or to noisy data. So that's why we introduced this penalized persistence. And we observe, if we compare the L1 penalty and the persistence penalty, that if we want to reconstruct, of course, it's better not to penalize the persistence, to keep a L1 penalty. But as soon as the train set becomes small and the level of noise becomes large, it becomes more and more advantageous to consider a persistence penalty rather than an L1 penalty. So this confirms the intuition we have, the heuristic intuition we had, that persistence penalized predictors offer good generalization properties. So yeah, these comments, I actually discussed them while doing the explaining the results. One thing we can notice is that we lose explainability while doing our method. So if we select the first, the second, the fifth, and the 10th eigenfunction of the Laplace Beltrami operator, that's good, but that's not really interesting here. Because one nice thing about the Lasso is that it enables variable selection, model selection. And if we performed it on the Euclidean space, well, the Lasso selected the pixels in white, and we recognize the shape of the cat. So we have an interpretation as what the Lasso is doing here. And we don't have this interpretation anymore. We only have it in terms of spectrum of the Laplace Beltrami operator, but it's something quite abstract. Okay, so if I still have some time, I can discuss the performance of the topological penalty. So Owen, interrupt me if we don't have time for that. So here the Lasso is actually quite simple to study because we look at an orthogonal design. The eigenvectors we picked, we can pick them in order for them to form an orthonormal family. And when we normalize them by their persistence, we have an orthogonal design matrix. And this is actually a very nice case, a very specific case of the Lasso, where we have an explicit solution, which is given here. And one thing to notice is this term y minus lambda chi divided by 2 xj transpose y plus. This is important because it's a threshold. Lasso acts as a thresholding operator here. More precisely, Lasso will select variables and will set a lot of variables to be zero, to be irrelevant in order to predict the response vector y. Here we have an explicit condition on whether a variable will be selected or not, so whether an eigenvector will be selected or not. So an eigenvector will not be selected if and only if the scalar product between the eigenvector and the response vector y is smaller than the trade-off parameter times the persistence divided by 2. This means that if a function has a very large persistence, it will need to significantly explain y in order not to be discarded. We will only keep it if it's relevant to explain y. We can also notice that while doing so, we can actually tune the parameter lambda in order to control this trade-off between explaining y and having a large persistence. And we can also tune lambda so that we can discard all functions with a persistence larger than some value. So here I'm going to describe a bit more precisely how we could prove that this function reduces overfitting. So we have this very, very important inequality in statistical learning that states that if we want to learn data y on data points x using some function h, the error we have in expectation is lower than the attachment to the data, so the empirical loss on the data points, plus some terms that depend on the function class h in which we pick the candidate small h, plus a term that depends on the confidence level we give ourselves. And this last term tends to 0 as n tends to infinity. So we will only focus on the first two terms. And we have actually here in statistical learning, we have everything is about picking the right class of functions. And this is a trade-off between picking a class of function. So yeah, basically, if the class of function is large, it's nice because we will have a lot of candidates small h, and we will be able to minimize this empirical risk. But this quantity Rn of h will be large. On the contrary, if we take a small class of function, we won't be able to find a good candidate h, but this term Rn of h will be small. This term Rn of h is called the Rademacher complexity, and it's actually the correlation of a signal h of xi to a white noise. Here the sigma i's are Rademacher variable, so basically Bernoulli variables, but in -1, 1 instead of 0, 1. And a class of function has a large Rademacher complexity if it has a large correlation to white noise, if it is able to learn white noise. And we don't want functions to learn noise. We want functions to learn data. So having a large Rademacher complexity will be a synonym of overfitting. And as this quantity is quite hard to control, we have tools to control it in terms of covering number and fat shattering dimension. So I don't think I'm going to develop that much here, but one preliminary result we had is that in one dimension we can control the Rademacher complexity of the class of bounded total variation. And I recall that in one dimension the total variation is the same thing as the zero persistence. It's the difference between the maxima and the minima. The problem here is that if we look at higher dimensions, if we look at functions that have a persistence lower than some value in all dimensions, well, unfortunately, this set is too big. We would have to restrict this set because as of now, these sets have an infinite fat shattering dimension, and we cannot control their Rademacher complexity. We cannot bound them, so we cannot state anything yet. So what we would have to do is restrict this class of function to a smaller class of functions, where here we could compute the fat shattering dimension, the covering number, the metric entropy, any nice statistical property. And it would be nice to do it so that the fact that we bound the persistence on these functions enable us to improve the bound we have on the function f. Maybe there's a thing, it's the third point here, is that the topological persistence just acts as a tool here, where as a computational tool, where by penalizing the persistence, we actually penalize some quantity that quantifies the regularity of the function class. We know that if functions have regularity assumptions, they will have a small persistence. We can bound their persistence, but I don't think that converse results hold. So this could be something to investigate, maybe in the case of the eigenfunctions here that are very smooth and regular functions. And it would be also nice to study directly the discrete case. So to conclude, I'm going to be busy with this project for the following 3 years, hopefully. I found this project I did with Wolfgang and Krishna that I'm continuing with Gilles and Clément very interesting in a sense that it's at the crossroads between a lot of different areas of mathematics that has apparently no connection between them. So I've done statistical learning, spectral theory, functional analysis, TDA, graph theory, many things. But this comes at a cost, of course, is that this problem has proven to be quite hard, to be quite challenging at some times. And every time we want to prove something new, we have to get our hands in mathematics I'm not necessarily used to do. One of the difficulties is that most results here are brand new, especially the use of this topological penalty, and having theoretical guarantees on this topological penalty is new. And the combination between the topological penalty and the Laplace Beltrami eigenfunction is something new as well. And here, yes, we can also say that I've conducted a few experiments, but it would be nice to conduct more experiments, especially on real data, on more maybe more interesting data from real life cases. I thank you for your attention, and I leave you with a few pictures of my trip to the US. So although I've not been able to go to Davis because of the pandemic, I've still been able to enjoy this interesting country, which is the United States. Thank you for your attention, and feel free if you have questions.